Welcome to this online class. I am Barnabas Mogo from Kitui campus, and I'm responsible for taking you through this online class. So today I want us to look at what we are supposed to do in structural mechanics 2. And if you remember well that we did structural mechanics 1, it involved the issue to do with the structure elements like the bedding or the bed, the beam, the column, the foundation, and also the footing. We looked at how you can be able to use or calculate the forces, the stress and the strain. And we also looked at different components that are involved in the structure. The structural mechanics 2 is just a combination, or it is just a continuation of what we were doing in structural mechanics 1. And therefore, without wasting time, I'm going to look at the first topic, which is theory of the simple bedding 2. And when we are looking at the theory of the simple bedding 2, we are looking at the theory of pure bedding. When you talk about the pure bedding, it is the bedding that is involved, that is the bedding moment. In this case, we don't involve the forces that are acting in it, but then the stresses, it is a condition whereby the stress is the one that is bringing the bedding moments that is applied on the beam. But we don't have anything to do with the shear forces. The shear forces has been eliminated in this case. So even without the presence of the axial, the shear, and the torsion forces, we can still have the bedding moment applied on a beam or coming in the beam. There are some assumptions that we need to make when we are doing the simple bedding, or when we are coming up with the simple bedding. One of them, we assume that the beam is straight and it's of uniform cross-sectional area, meaning that the beam is not curved, the beam is always straight. And the X, the Y, and the Z axis have equal dimensions. We also assume that the beam is homogeneous and isotropic, meaning that homogeneous is made of the beam is made of the same material, and isotropic, it means that the beam is it has the same elastic properties in X, Y, and Z election. We are also assuming that the resultant of the applied load lies in the plane of the symmetry. That is the resultant weight, the one that is applied. It lies on, it is symmetrical. The plane is symmetrical along the resultant point. That is the resultant weight, or the resultant weight is being applied. We are also assuming that it is only the bedding moment that is making the beam to fail, but not collapsing or buckling. We are also assuming or making an assumption that the plane remains plane either before and after bedding. It does not change the cross-section dimensions. We are also assuming that the Young modulus, or the modulus of elasticity, is the same either we have the tension or compression. We are also assuming that the rear, that is the beam, is made of different layers, and each layer is in position of expanding and contracting independently of the other rear. We are also assuming that the radius of the curvature is larger as compared to the cross-section dimensions, as we are going to see later. The radius of the curvature, when you bed the beam, we are going to have the curvature. That is the center of the curvature, because it is going to look like an arc, and that the beam is going to look like an arc, and therefore the radius of the curvature is going to come from the center of the curvature to the neutral axis. So we are assuming that the radius of the curvature is going to be larger as compared to the cross-section dimensions of that beam. We are saying that homogeneous means that material is made of the same kind throughout, and that isotropic, the elastic properties in all directions, that is the X, Y, and the Z ordinates, are equal. Then we are supposed to look at the moment of resistance. And when we are looking at the moment of resistance, we are going to see that it is the algebraic sum of all the internal forces about the neutral axis. The algebraic sum of the internal, or the sum of moments in the internal forces about the neutral axis, either on the compression side or on the tension side. When you add all the internal forces, that is the moment, the internal, the sum of moment in the internal forces from the neutral axis, that will constitute to what is called the moment of resistance. And for us to have an equilibrium condition, the moment of resistance of the section, we are saying that they must be equal to the bending moment at that section. And when we load the beam, as you can see in this diagram, or in that section of the beam, if the topmost part of the beam is going to experience the force of compression, while the bottom part is going to experience the force of the tension. And when we have the compression and the tension forces acting in this beam, at the topmost part, we are going to have layers becoming short, as you can see in this side. Shorter layers can be observed. But at the bottom part, where we have the tension, because there is pulling of the grains, then we expect to have the longer section being experienced. So the layer at the top, the layers at the top is going to shrink, and while the layer at the bottom is going to elongate. The moment of resistance equation is given by this equation that you can see here. It is also the bending moment equation. Reason being, we have just said that the moment of resistance is equals to the sum. That is, the sum of the moment of resistance is equals to the sum of the bending moment. And therefore, they are going to share the same equation. The first parameter is the stress of the grain along from the neutral axis. So at the neutral axis, we are going to have the stress of the fiber at the center Y from the neutral axis. Fibers are those layers. So you are going to take a layer and you are going to get the distance from the distance from the neutral axis. That is the stress from the neutral axis. Y is the distance from the neutral axis, which is the center of that beam. M is the bending moment. I is the second moment of area, or the moment of inertia. And we said that if it is a rectangular section, it is going to be BD cubed over 12. Then E, capital letter E, is the Young modulus of the material, and we know that the Young modulus is given by stress over the strain, while R is the curvature radius of this bent beam, as we are going to see in another diagram. So if you can observe this diagram, you can see the value of R here. It is from the radius of the center of the curvature to the beam, the neutral axis of the beam. M, as you can see here, is the moment of the bending moment. Y is the distance of the layer from the neutral axis. Neutral axis is CD, while the layer that we want to check is layer AB. And therefore, Y is the distance from the neutral axis towards that layer AB, as you can see also from the first diagram. We are then expected to be able to come up with the general equation of the bending moments. And when we are looking at the general equation of the bending moment, it is also called elastic friction formula. And I have said that the bending moment equation is the same as the equation of moment of resistance. And therefore, we are supposed to be able to come up with this equation in the derivation. And as I have just talked about in this formula or in this diagram, we have diagram number A where the beam is initially straight. We have just said that. And the beam is unstressed, meaning that there is no force that is acting on it. And then on the same note, we have when there is loading, we can observe that the beam is going to bend, as you can see from the diagram number B. And we have different parameters such as R, which is the radius of the curvature, M is the moment, or that is the bending moment, Y is the distance from the neutral axis, which is CD, and AB is the rear under the consideration. Because we cannot be able to derive this equation online, well, as you can do with your lecturer in different campuses, I would prefer that you inquire from your lecturer when you go to face-to-face or when you have face-to-face class. He or she can be able to give you the derivation, or you can derive the equation with him or her, so that you can take the fiber AB and you get the strain. We say that the strain is the change in length to the original length. AB, that is A prime, B prime minus AB over AB is going to give us the strain of that material. AB is the initial length, and AB, that is A prime, B prime, is the final length in B. That is in diagram number 1B. So we get the strain. And then after getting the strain, we are supposed to get the strain of the neutral axis. Then we compare the two, because the strain in the neutral axis is not changing. Then from there, you are supposed to come up with this parameter. Because you cannot be able to live online, I'm going to request you that you talk to your lecturer. Then you know that the stress and the strain is going to give us the Young modulus. And then from there, you equate the equation as necessary. And then from there, you consider another layer from the neutral axis. And then from there, you equate to the value of M, and then you get the neutral axis. This equation can only be done when you go to face-to-face class. So just bear with me. Then from there, we are supposed to talk about the fixed beam and also the composite beam. Fixed and the composite beam, we say that the fixed beam, that is the composite beam, is a structural element consisting of two or more materials of different mechanical properties that have been joined together. That means that if I have a concrete, that is a reinforced concrete, reinforced concrete will act as a composite material, because the reinforcement material and also the concrete material, they are acting as one component and they have been joined together mechanically. Then fixed material include those materials that have been joined either by riveting or by nailing. That is, they are dissimilar in nature, but then they have been riveted together. This is an example of a composite material. It is rolled, as you can see from this diagram. That is, we have the compression side and we have the tension side. It is a simply supported beam in the sense that it is supported at the edge by those two black triangles. As you can see, there is the saber. And then it's a reinforced material, meaning that it has the steel part and it also have the compression side, as you can see, these are the components that are making that structure. And then we needed to know how to come up with the modular ratio of the composite material. And as you can see from this diagram alongside, we have the wooden section that is in between the two steel parts. And then we need to know that y is the distance from the neutral axis to the furthermost part or to the edge of that plate. And then b is the breadth of the wood. T is the breadth of the T that you can see here is the breadth of the steel parts. And then D is the distance, that is the depth of the two materials. The first thing when you want to be able to compute the stress and the strain is to be able to compare the two. That is, we know that the modular ratio, that the modular is going to be given by, that is the modular of the elastic or the composite material. First of all, you need to calculate the strain. The strain, we know that it is the stress over the Young modulus. And what we are saying is that the composite material, the stress is going to be the same, either in this case in the wood or in the steel plates. And therefore, because it is going to elongate the same, it means that the stress in the wooden section, that is load W over EW, is going to be the same as that of the strain, that is of the steel plates. And therefore, stress over the strain is equal to the stress over the strain. Stress in wood over the strain, that is the Young modulus of the wood, is going to be the same as the stress in case of the steel plate over the Young modulus of the steel plates. And therefore, you are going to get the strain of the two materials. What do I mean? I mean that when we are looking at the issue to do with the strain in a composite material, it is going to be given by the strain of the one material is equals to the strain of the other material. And therefore, low W over EW is the strain in the wooden section, and it is equals to low S over ES, the strain over the steel plates. You can inquire further from your respective lecturers. And then from there, we need to know how to determine the moment of resistance of a composite material. And if you remember well, that we said that an expression for the moment of resistance for steel and wood in the beam above is determined by, one, you take the moment of resistance, that is the stress, you multiply by the lever arm. And therefore, if I want to know the moment of resistance of the wooden section, it is stress of the wood, the one that you can see, over the lever arm. The lever arm is BD squared over 6 in this case. So you need to get the information well. Then from there, you need also to get the moment of resistance of the steel section. It is the stress of the steel section you multiply by the lever arm of the steel section. And therefore, in our case, it is going to be the PS, which is the stress of the steel parts. You multiply by TD squared over 6 times 2. The reason as to why we are multiplying by 2 is because we have two steel plates on the left and on the right hand of the wooden plate, as you can see from that diagram. Then from there, we need to remember that the stress of the steel or one material is going to be given by the moment of resistance you multiply by the stress of the other material. So that is exactly what we are doing. That is, if I want to determine the stress of the steel, it is going to be the moments, the moment of resistance I multiply by the stress in case of the wood, as you can see. And therefore, I just replace that information in this equation by, I get the stress, that is, I equate, or I know I equate PS from the moment of steel in order for me to be able to get the moment of the steel when I have the component of the wooden section, as you can see from that diagram. So it's just replacing PS with MPW. Then from there, the moment of resistance of the entire beam is going to be given by the moment of the wood you add to the moment of the steel. So I get the equation of the wooden section, and then I add to the equation of the moment of the steel part. Moment of the wooden section, I add to that of the steel section, and that equation is going to give us the moment of resistance of the whole section. Then from there, I need to be able to come up with deflection of the simple bedding, the moment of the simple beam. So when I'm looking at the deflection of the simple bend or simple beam, I should know that the deflection of the simple beam, it involves different parameters. That is, when I load a beam, an initial straight beam will always bend. As long as there is loading of the beam section, we expect that there is some deflection that is going to occur. There is a bending that is going to be experienced by that beam. And therefore, the shape of the bend is going to give us the deflection curve of all elastic curve. And therefore, we are going to define the deflection at a point on the axis of the beam as the distance between the position of the point before and after deflection. You get the distance or the position of the point before and the point after deflection, and then you get the distance between the 2 points. They are going to constitute to what we are calling the deflection. The slope, on the other hand, is going to be the angle between the tangent of the point and the axis of the beam in its undeflected state, as you are going to see later. What are some of the effects of the deflection? One of them is that the bending and dislocation of the initial point of the beam. When the beam deflects because of the loading, we expect that the initial point is going to deflect, or it is going to be different from the final points. We also expect that the cracking of the beam, if the elastic limit is reached. If the elastic limit is reached, we expect that there is going to be cracking of the beam, and then the stress induced by loading develop within the beam matrix. That is also another point that we need to know. Then from there, we are also expected to be able to calculate the general equation for deflection. This is also another hectic thing to do in online, but I would also request that you go to your respective lecturers in different campuses and discuss with him or her pertaining to how you can be able to derive the equation pertaining to the that is the general deflection equation of deflection. That one I'm going to make sure that I talk with your lecturers so that you can be able to derive the equation effectively during your face-to-face class. But generally, we can therefore summarize the equation as the bending moment is going to be given by m, and then when you do this, the deflection coefficient will be ei dy squared over dx squared, and the integral will be m. The slope is going to be given by dy over dx, and deflection is going to be given by capital letter Y. You are going to, I'm just going to give you the methods that are going to be used in determining or calculating the slope and deflection. But the general equation for deflection, you can just utilize your face-to-face class in order for you to be able to catch up with what you are supposed to do. There are two methods that we can use to calculate the slope and deflection of any objects or the deflection of a beam. One of them is called Macquarie's method. It is also called double integration method. The other one is called the Moore-Theorem method or the moment area methods. We are going to look at each one of the case and determine how you can be able to use in its computation. In the Macquarie's method, all the double integration method, this is a method that is utilizing two integral of calculus. That is, you integrate the first time and you also integrate the equation in the second time. The first time is going to give us the deflection, while the second time is going to give us the slope. That is, no. But the first time is going to give us the slope, and the second one is going to give us the deflection. It uses the general equation, the one that I have just talked about here, the one that we are going to derive with your lecturer. This one, it uses the general equation, this one that we are going to derive with your lecturer. It uses the double integration methods or formula for calculating the slope and deflection of all the beam. That is what we have just seen. And to apply this method, there is something that is called the double or the boundary conditions, which you are supposed to set in order to determine the slope and deflection. And therefore, we need to know that deflection at the support are assumed to be zero. Deflection at the support is going to be assumed to be a zero unless otherwise stated. Then the slope at the built-in support are assumed to be zero unless otherwise stated, meaning that the deflection and the slope at the support, if you have a simply supported beam at the location or the point whereby the support are acting, both deflection and the slope is assumed to be zero. Another thing that you need to know is that the slope at the center of symmetrically loaded and supported beam is zero. Because we have the maximum deflection at the center when you have a simply supported beam, we are assuming that we need to assume that the slope at that center of symmetrically loaded beam is also zero, because it is, we are taking against the tangent, and the tangent at a flat section, the angle at that section is assumed to be zero. Then the bending moment at the free end of the beam, those not built in, is also assumed to be zero, as we are going to see. In order for us to understand fully, we needed to come up with certain equations. We needed to come up with certain equations. We need to come up with this equation. This is a cantilever beam, and in this cantilever beam, you can see that we have a section XX, it is loaded with W1 and W2 at B and C point respectively. C is a distance L1 from the fixed point A, while B is L value from that fixed end, and the cross section point at the cross section, it is a distance X. So if you take the section X from the neutral axis, that is not from the fixed end, the bending moment is going to be given by this formula, because we are taking the X section XX, as you can see, the value of XX. Then the moment at X is going to be given by, we say that moment is distance times the force. We have force W1, the distance at X, at the moment at X is going to be L U minus X. L times W1 times L minus X. L minus X is the distance from the cross section XX to the point B. Then you are supposed to add to W2, you multiply by L1 minus X. L1 minus X is the distance from C to cross section XX. And therefore, we need to know that moment is going to be given. We have just said that this is the general equation for the bending equation. And therefore, we are saying that we are utilizing this general equation. And therefore, our mx is going to be replaced by ei dy squared over dx squared. That is, in Macquarie's, we have just said that we are utilizing the equation for the general bending. And therefore, it is going to be equals to whatever is on the right hand side. As you can see, this is, we have just replaced this section. That point, I just put it on the left hand side like that. But then mx, this one, I'm going to carry it with the red. It is going to be replaced by this one, reason being equation for the bending moment is that one. We are replacing the greenish part with the reddish part. So the left hand side of that equation is going to be those parameters. Then we needed to integrate this equation. And when we integrate the first time, when we integrate that equation, the first time, we are going to get the slope. You can use slides, different people like your calculus lecturer or your class teacher, subject teacher, in order for you to be able to know how to do the calculation or to know how to do this calculation. So integrating the first time is going to give us the slope, and then if you integrate the second time, it is going to give us the deflection. The slope is given by whatever you see on the left hand side is going to be the symbol for abbreviating the slope, and y is going to be the second. Is going to emerge from the second integration. So these are the equation as they are going to see. You can utilize your lecturer for more information. Then we can also have a simply supported beam. In this case, it has a varying loading, that is uniform varying load. And then we take the same cross section XX, and we determine the moment at that section. This one you can do with your lecturer, because it is not possible for me to be able to do it online. But whatever I'm going to say is that the first integral is going to give me the slope, and the second integral is going to give me the deflection. So that is how you go about doing or coming up with the deflection of the simple, that is the deflection and also the slope by use of Macaulay's or double integration method. The first integral is going to give you the slope, and the second integral is going to give you the deflection. And another thing that I want you to know is that we are utilizing the equation for the bending moments. So you just need to follow the instruction, and for more information you can inquire from your lecturer. Then from there, you need to know how to come up with the Moore theorem. This is the moment area method, or it is also called the moment area method. It is also used in determination of the slope and deflection of a loaded beam. And therefore, when you have the loading, moment, that is the theorem 1, it states that the slope between any 2 points on a deflected beam is equals to the area of, that is M over EI diagram, the moment area diagram of that section, And therefore, what you need to know is that the first theorem is going to give me the slope. All it's supposed to give us the slope. The second theorem is going to give us the deflection. So when we are looking at the theorem, they are two, theorem 1 and theorem 2. Theorem 1, it states that when you have 2 points that are in deflection, that is that in a deflected beam, the area that you can be able to calculate between the two slopes is going to give me the slope of between the two sections. The area between the two sections is going to give me the slope of that section. You can inquire more from your respective lecturer. For more information, you can see page 243 in Material and Structure, book by Al Whitelaw. The second theorem is to do with deflection, or it is applied in deflection. And it states that the deflection on a point in a beam, it is relative to the tangent of another point on the beam is equals to the moment of M over EI diagram between the 2 points. This one you can get it more information from your lecturer. So I'm not willing to do more in deflection and derivation of the equation because it looks somehow a challenge to do it online. So you can just get this information from your lecturer. You derive with him during your face-to-face class, and then I'm going to post some equation or some calculation in order for you to be able to practice or to do some practice effectively. But generally, the Moore theorem is applied in different categories. That is, for the cantilever of length and under the load with the free ends. I think you can just do it with your lecturer because it is not possible to do it online. You can also see how to do it, that is the cantilever under UDL over the entire beam, and then for a simply supported beam. So that is the first topic. That is what you are supposed to cover in the first topic. I'm going to talk with your lecturer so that you can be able to derive those equations during your face-to-face class. Thank you for coming. During our online class, the actual online class, I will be able to answer your questions or the questions that you might be having in this video content. And then we are going to continue with the second topic Thank you. Thank you.